All right, today we're diving into something that feels like it's pulled straight from science fiction, but it's actually grounded in some seriously cutting-edge research. We're talking about a power grid that isn't built, it's grown. Let's explore the blueprint for a grid that is quite literally alive. Just take a second and really chew on that question. Forget concrete and steel for a minute. Imagine instead a network of living microorganisms, all working together, generating power, healing themselves, and adapting to threats in real time. This isn't just a fantasy, it's the subject of some truly mind-bending work.
And this quote right here, this is the heart of it all. This is the grand vision, pulled directly from the research. The goal isn't just to make a new type of battery, it's to prove the viability of a self-governing, intelligent, living energy system. A system that can basically think for itself.
So how in the world would that even work? Well, the core technology is called biohybrid energy. To put it simply, it's all about using the natural ability of certain microbes to pass electrons around, which, is the very essence of electricity. We're talking about creating a true symbiotic relationship between living biology and our electronics.
Now, obviously, before you can grow a living grid, you have to design it, and that's where the mythic biogrid comes into the picture. Researchers built this incredibly sophisticated computer simulation to model the whole idea, creating a virtual world where they could test how a living system like this would actually behave.
So inside this simulation, they created 3 different types of agents. You can think of them like digital microbes, each with a very specific job. First up, you have the healer, whose #1 goal is keeping the system stable and cleaning up any junk. Then there's the trickster. This one is the high-risk, high-reward agent that just goes all in for maximum power output. And finally, you've got the builder, which is focused on one thing, growing the network and making more of itself.
Okay, so you've built your virtual living grid. What's the next logical step? You try to break it, right? To find out just how tough it was, the researchers threw a series of brutal stress tests at their creation, which they called rituals.
First, they tested some simple, static designs that couldn't change. And what's so cool about this slide is it shows there's no single perfect design. The lattice structure with all those extra connections was fantastic at isolating a threat, like a disease they called contagion. But the spiral design was way better at managing resources when things got scarce, during a famine. You see the problem? Each one had a fatal flaw.
And that sets up the ultimate test, the big one. What happens when you hit the grid with both disasters at the exact same time? A localized infection and a system-wide resource shortage. This is the perfect storm, a scenario engineered to cause a complete cascading failure.
So how did that static lattice design hold up? Well, it suffered four total systemic crashes. The healers tried so desperately to fight the contagion that they burned through all the scarce resources, which ended up starving the tricksters that were making the power. The whole grid just collapsed.
But then, they ran the test again, this time with a dynamic, hybrid design, one that could actually change its shape and strategy on the fly. And the result? 0 crashes, not one. It's just a brilliant illustration of the power of adaptation. The system survived the exact same perfect storm that had totally wrecked its static cousin.
So what was the secret sauce? It was something they called the Evolutionary Protocol. This basically gave the grid a brain. It allowed the system to recognize what kind of threat it was facing, and then completely shift its internal strategy. It could tell its agents when to hunker down and save energy, and when to go on the attack and crank out power. In other words, it could evolve.
So, the simulation was a massive success. It literally provided a working blueprint for a resilient, living energy system. Which brings us to the next and, let's just say, the very important part of our story. We're about to see what happens when this incredible dream collides with cold, hard reality.
I mean, it's a fantastic idea on a computer screen, right? But what does it actually take to pull this out of the simulation and build it in a lab? What's the real-world price tag on a self-evolving grid?
Well, the really detailed feasibility report breaks it all down for us, and it turns out creating a system that mimics life comes with some pretty serious financial pressure points.
The costs really boil down to 3 main categories. First, and this is the big one, you have synthetic biology services. That's the price of actually engineering the microbes. Second, you have the high-purity materials you need for the physical structure. And third, all the capital equipment you need to build and test the whole thing. To give you a sense of scale, let's just look at that biggest slice of the pie. The report estimates that designing a single, complex genetic component that's just one piece of the microbial puzzle could run you almost $4,000. And here's the kicker. In synthetic biology, your first design almost never works perfectly. Biology is messy, it's complicated, it's often unpredictable. So what happens when you have to go back to the drawing board?
Well, the costs don't just add up, they multiply. That initial $4,000 investment can easily balloon to $12,000 or more after just a few cycles of designing, building, and testing. This process, this iteration, makes synthetic biology the single biggest financial risk in the entire project.
What's so fascinating about this slide is the story that it tells. Ordering raw DNA, the basic code, it's incredibly cheap. We're talking cents per letter. But turning that raw code into a complex, functional genetic circuit that you can reliably stick into an organism and have it work, that's where the price just skyrockets into the thousands.
And it's not just the biology either. The physical stuff, the parts you can actually hold, are surprisingly expensive too. The high-purity carbon felt they need for the electrodes can cost thousands of dollars for a single roll. The special carbon nanotubes that improve conductivity are sold by the gram for hundreds of dollars. Even getting specialized labor for custom 3D printing can cost you up to $200 an hour.
Okay, so it's an amazing idea, but it's also incredibly expensive. Does that mean it's a dead end? Well, not at all. The feasibility report doesn't just point out the problems. It also lays out a really clear strategic path to move forward.
The key is to be smart about it. You don't build the whole thing out of the most expensive materials. You use them surgically, only at that critical spot where the microbe actually touches the electrode. You use cheap sensors for 24/7 monitoring, and only bring out the expensive, high-end gear for targeted analysis. And most importantly, you focus your genetic engineering efforts on the two things that matter most: that physical connection and the communication system that lets all the microbes work together as a team.
So what's the bottom line? If you follow that smart, strategic blueprint, the report estimates that the cost to build the very first research prototype would land somewhere between, let's say, $19,000 and $38,000. It's not pocket change for sure, but it puts a real, tangible number on turning this incredible simulation into a physical reality.
And that's really where this whole thing leaves us. The science, the simulation, it's all shown that a self-governing, adaptive, living power grid is actually possible. We have the blueprint. The barrier isn't our imagination anymore. It's investment. So the real question we have to ask ourselves now is, are we prepared to pay the price, not just to build our future, but to grow it?
Welcome to the Deep Dive. We're the show engineered to take, well, frankly, a complex stack of research. Everything from these elegant computational simulations right down to the hard-nosed financial assessments, and really distill it down to the critical core, just for you.
And today, we're attempting something pretty ambitious, I think.
Definitely ambitious. We're trying to bridge this huge gap, moving from a purely theoretical design of a self-governing energy system
all the way down to the, let's say, the synthetic biology budget, the actual costs needed to embed that kind of intelligence into living microbes. It's quite the leap.
It really is.
But it's an essential journey, wouldn't you say? Because we're navigating, well, a fundamental paradigm shift here.
How so?
We're moving beyond just talking about, slightly better batteries or maybe cleaner solar panels. We're diving headfirst into what the sources are calling the symbiotic energy imperative.
Symbiotic energy imperative. Okay.
Yeah, systems that are deeply integrated with natural processes, specifically things like microbial or photosynthetic electron transfer. It's the ultimate biohybrid energy system by definition.
Exactly. And that means the core intellectual challenge is shifting quite dramatically.
Totally.
We're no longer asking the old question, how do we make one single cell maybe 10% more efficient?
Right. That's almost become secondary.
Instead, the sources we're looking at today focus squarely on how do we make the entire system resilient, self-governing, capable of long-term survival, even under significant stress.
It's that pivot away from purely extractive tech towards integrated natural processes.
And that resilience, it's not just a fuzzy concept, is it? It's quantified.
Oh, absolutely. There's a highly specific metric they use, system resonance, or GLEAT.
Wow.
Think of it as a holistic measure. It captures the grid's simultaneous stability, its efficiency, and its metabolic health all in one number.
So if KEAT is high,
the system isn't just generating power, it's actually thriving. It's robust. But if CEAT collapses, Well, the whole system is crashing.
And the crucial part.
The crucial part is that maximizing this seat, this system resonance, it doesn't depend on just boosting individual cell output. It's all about the system-level architecture and the collective coordinated behavior of all its parts, all its agents.
Got it. So that sets up our mission for this deep dive pretty clearly.
It does.
First, we need to unpack the computational blueprint. This thing details the core theoretical design, which is known as the Evolutionary Protocol.
And then, straight after that, we pivot. We hit the hard financial and technical reality check. That comes from the feasibility report.
The cold hard cost, basically.
Yeah.
Translating that elegant protocol into a physical, functioning, living biogrid prototype.
Let's start with that blueprint then, the computational side.
Sounds good.
We're looking at data from a really novel multi-agent computational simulation. It was developed by Skylar Fiction.
Skylar Fiction, okay.
And they built this model specifically to test resilience and adaptive capacity in these distributed bioenergy grids. They actually refer to it sometimes in their documents as the mythic biogrid simulation.
The mythic biogrid. I like that. It sounds appropriately ambitious.
It does, doesn't it? Because it represents the goal, the optimal self-healing, self-governing system.
And important to note, the ultimate goal of this simulation, it wasn't just about maximizing power output, was it?
Not at all. It was about designing a system so intelligent, so robust, that it could dynamically adapt its whole metabolic strategy, what they label sigma, the Greek letter sigma.
Okay.
And it adapts that strategy based on whatever environmental threats it's facing. We're essentially talking about programming self-governance into a colony of microbes.
Wow. Okay. And the ultimate measure of success for this simulation, the final grade, so to speak.
That would be achieving a high adaptive coherence index, or ACI.
ACI, another key metric.
Exactly. Think of the ACI as the final report card for the whole simulation run. It synthesizes resilience, efficiency, stability. It quantifies the system's ability to survive and keep functioning under cyclical, complex stress over a long period. A high ACI basically validates the entire underlying design, the whole architecture.
Okay, let's unpack this architecture then. It sounds pretty sophisticated. The simulation uses these things called bionode agents, or BNAs.
Correct. BNAs, they're situated in a 2D discrete grid, like squares on a checkerboard, basically.
But they're not all the same, are they? They have different behaviors.
That's the key insight. They're not generic. They're governed by these defined behavioral strategies the designers call archetypes.
Archetypes. This is where that idea of metabolic ethics comes in, right? Programming a sort of philosophy into each node.
Precisely. They defined 3 distinct archetypal agents. This was deliberate to ensure the grid wasn't just some monoculture obsessed with maximizing one resource. It had built-in diversity, even strategic conflict.
Okay. And each archetype prioritizes a different metabolic output strategy. That sigma is the value we mentioned.
Exactly. Sigma determines their contribution, but also their consumption patterns within the grid. It defines their role, their ethic.
Let's detail these archetypes then. They seem crucial for understanding how the system controls itself later. First up, the healer. What's its job?
The healer's metabolic ethics, if you will, prioritize mitigating toxin and ensuring overall metabolic stability. Its core function is defense.
So its sigma value.
Its sigma dollar is inversely proportional to volatility. It actively suppresses dangerous energy spikes and allocates resources towards detoxification. Think of it as the system's defensive backbone. It will sacrifice short-term electrical output for long-term health, for keeping that system resonance set high.
Okay, makes sense. Defense first. Then you got the trickster. Sounds like the polar opposite. High risk, high reward, maybe.
That's a perfect description. They are the performance drivers. Tricksters prioritize high, spiking electrical output. They maximize short-term power delivery, which gives you these bursts of high efficiency.
But there's a catch.
Oh yeah, big catch. Their aggressive consumption strategy makes them really vulnerable. They are prone to systemic failure, a complete crash, if their internal fuel reserve drops below a specific minimum threshold. They call it phi min.
Moving fuel level.
Right. They represent, in a way, the high-demand, high-performance parts of any modern electrical grid, necessary but potentially unstable if starved.
Got it. And rounding out this trio is the builder, focused on expansion.
Correct again. The builder's sole purpose is self-replication and system expansion. It allows the grid to physically grow to occupy available space on that 2D grid.
Is it always building?
No, it's dependent on conditions. It needs specific, favorable local conditions like high resource abundance and low localized toxin levels to successfully spawn new nodes. So it only pushes for growth when the overall environment is healthy enough to actually support it.
Okay, 3 archetypes. Healer for defense, trickster for risky performance, builder for conditional growth. Very clever design.
It really is. And the genius then moved to testing how these agents interacted and how different physical arrangements or topologies affected the system.
Right. Through these things they called rituals, which are basically scripted environmental disasters for the simulation.
Exactly. Stress tests designed to break the system in specific, informative ways.
So the first test, Ritual 1, famine, run number 003 in their logs.
Yeah, famine. This was a purity test, really, focused purely on resource flow efficiency. They simulated a global, prolonged decline in the fuel supply. Maximum efficiency was the only way to survive.
And the key finding.
Conclusive. The spiral topology, which offers a very direct, efficient pathway from where the resource comes into all the nodes.
Like a single winding road reaching everyone?
Kind of, yeah. That spiral was about twice as efficient for resource flow optimization compared to the other main topology they tested, the lattice.
Okay, what's the lattice like?
The lattice is more like a grid, a mesh. Lots of connections, very redundant, good for some things, but not for pure speed of delivery.
So if resource scarcity is your only worry, spiral wins. Simple, direct flow.
Exactly. But that finding was immediately challenged by the next test.
Ritual 2, contagion. Run 004. What happened here?
Well, contagion was completely different. It involved a localized, high-magnitude spike of toxin, which then spread rapidly. Suddenly, efficiency wasn't the main concern. Isolation was.
And that super efficient spiral pathway.
Becomes a superhighway for the toxin, too. It moves it just as fast as it moves resources. Bad news in a contagion scenario.
So the lattice.
The lattice topology, with all its redundant pathways and distributed nature, proved far superior for detoxification. It could contain the spread better, it minimized the healer sacrifice, how much energy the healers had to burn to clean up, and it maintained a higher system resonance. The network structure itself helped isolate the threat geographically.
Okay, that immediately proves a crucial point. No single static architecture, no single topology is good enough for a robust, real-world system that faces multiple kinds of threats.
Precisely. It forces a core dilemma onto the system designers. You can optimize for resource flow, or you can optimize for defense, but doing both with one simple structure seems impossible.
And they really hammered this point home with the next ritual, didn't they?
Oh, absolutely. The perfect storm ritual. Run 005. This was the ultimate stress test. They overlapped a severe famine and a contagion simultaneously, specifically designed to trigger cascading failure.
And this is where the sort of philosophical design of the archetypes meets the harsh reality of the topology, the pure lattice topology, the one that was good at defense. It failed.
Failed systemically. The logs showed 4 catastrophic trickster crashes.
But why? If it was good at defense against the toxin?
Because the very act of defending caused the failure in the famine context. Think about it. The healer agents went into overdrive, consuming huge amounts of energy to neutralize the spreading toxin. They succeeded in defending.
But that defense drained the global energy pool.
Exactly. It drained the overall metabolic pool just enough to push the tricksters below their critical bath threshold. Boom. They crashed.
Wow. So the system's own protective measure, the healer activity, ended up causing the productive component of the trickster to collapse because of resource depletion caused by the other crisis, the famine.
Defense caused failure in that suboptimal architecture. It's a really powerful conclusion, I think, about these hidden architectural traps, not just in biology, but in any complex system design. It's a universal problem.
A system design catch-22. You defend against one threat, you become vulnerable to another.
Perfectly put. So the solution they developed, logically, was the hybrid topology.
Combining the best of both.
Exactly. They merged the strengths. A spiral core in the middle, optimized for that efficient resource flow, surrounded by a robust lattice shell on the outside, dedicated to toxin defense and containment.
Best of both worlds. And the results.
Stunning, actually. This hybrid structure completely avoided systemic collapse during the perfect storm. 0 crashes recorded. And maybe just as important, it drastically reduced the healer sacrifice by 87% compared to the pure lattice that failed.
So the hybrid preserved that crucial system resonance, see, even under maximum combined stress.
Yes. That structural fix, the hybrid topology, provided the necessary resilient foundation. But structure alone only gives you resilience, right? It doesn't give you intelligence.
Okay, so resilience is step one, but not the final goal.
Correct. To maximize resilience and efficiency simultaneously, especially under changing conditions, the system needed dynamic adaptation. It needed to think.
Which leads us directly to the next section, the validation of that intelligence layer, the evolutionary protocol.
Exactly. Now we're moving into, let's call it section 2, the brain of the operation.
Right. And the final key test here was the evolutionary protocol ritual, run 007. This one incorporated something called the shifter protocol, and this was embedded within the builder agents.
Yes, the builders took on this extra role. Think of the shifter protocol as the dynamic operating system for the entire grid. It's that ethical flexibility put into action.
How did it work? What did it do?
It enabled real-time recalibration of those volatile trickster outputs, their sigma values, based on precise grid-wide threat detection metrics.
So it sensed the overall state and told the tricksters how to behave.
Pretty much. It used 2 key thresholds. First, if the total toxin sum across the grid exceeded a value of 50, the system initiated a defense mandate.
Defense mandate. High toxin means play it safe.
Exactly. Second, if the global fuel level dropped below 100, it initiated an aggression mandate.
Aggression mandate. Low fuel means go get more, quickly.
You got it. Simple logic, profound effects.
Okay, let's analyze the results of that flexibility. When the defense phase was triggered by high toxin, what did the protocol do to the trickster's sigma?
It enforced sigma right arrow, 0.55 dols. Essentially, it forced the high-performing, high-consuming tricksters to throttle back their output significantly. This reduced their chaotic energy consumption and the overall system volatility.
And the systemic result.
Really powerful. They measured a 29% reduction in the total detox cost compared to the static hybrid topology running the same scenario without the shifter protocol.
29% cheaper. Why?
Because proactive throttling, telling the tricksters to calm down before things got totally out of control, meant fewer resources were ultimately spent on reactive cleanup by the healers later on. It validates a core hypothesis. Proactive control is inherently cheaper and more efficient than reactive defense when dealing with a rapidly spreading threat like toxin.
Makes perfect sense.
Yeah.
Okay, and conversely, what about the aggression phase? When global fuel got dangerously low.
In that case, the protocol enforced sigma right arrow 1 toll of $5. It pushed the tricksters to maximize their harvesting output, to aggressively pull in resources and restore that fellow buffer as quickly as possible.
Which sounds risky, given the trickster's tendency to crash.
It would be, in a less robust structure. But remember, this is running on the hybrid topology. Thanks to that underlying structural integrity, the spiral core feeding them efficiently, the lattice shell protecting the perimeter, the crashes were limited to only one very minimal late-stage event. The aggressive consumption could be initiated relatively safely because the foundational architecture was there to manage the inherent risk.
Wow. So the structure enables the strategy, and the strategy optimizes the performance within the structure's safety net.
Beautifully summarized. It's a synergistic relationship.
Okay, so the big conclusion from all this computational work, it comes back to that ACI score, the Adaptive Coherence Index.
Yes. The final ACI reported for the system running the hybrid topology with the active shifter protocol was 12.45.
Which is good.
Very good. It confirms that it wasn't just the static architecture, the hybrid, nor the raw output capacity of the agents that defined the ultimate success. The definitive factor was the internal ethical flexibility.
The ability of the agents, guided by the shifter protocol, to dynamically change their operational priorities. Defense versus aggression in response to the environment. That's what maximized resilience and performance under stress.
Precisely. The computational work, that mythic biogrid blueprint, it's essentially complete. They have the architectural guide, they have the operational protocol, the elegant mathematical proof is validated.
So the mandate is crystal clear now.
Crystal clear. The next monumental step is translating this shifter protocol, this dynamic operating system, from elegant computational code into stable, functional genetic circuits within the living bioagents, from bits to biology.
And this, as you flagged right at the start, is where we pivot hard.
Very hard pivot.
We leave the realm of, theoretical elegance, computational proofs, and we land smack bang in the middle of the technical and financial reality check, synthetic biology.
Yep. We now turn to the feasibility report, and let's just say its tone is far more sobering, especially regarding the financial implications.
A reality check indeed. So the report confirms technical feasibility for some parts.
It does, especially for the hardware side. Things like integrating low-cost, Commercial off-the-shelf COTS electronics for the control infrastructure, the monitoring.
Yeah.
That part looks pretty straightforward. Affordable, even.
Wow.
But the report identifies the primary financial and technical uncertainties as residing almost entirely in one single area: synthetic biology, symbio.
That's where the big question marks are. And the report calls out 3 specific things, 3 dominant financial pressure points that are going to govern the total cost of actually building this advanced research prototype. What are they?
Okay, number 1, specialized synthetic biology services. This covers the high cost of getting custom DNA vectors made, getting stable genetic circuits, operons built and validated. It's specialized contract work.
Right. Custom bioengineering.
Number 2, high purity material sourcing. Because the performance of these microbial fuel cells, or MFCs, is intrinsically linked to the materials used, especially things like high-grade carbon felt for the electrodes and carbon nanotubes, CNTs, for conductivity. Purity matters a lot.
Impurities could kill the microbes or ruin the electron transfer.
Exactly. And number 3, capital equipment investment for validation. You need specialized gear to actually test if the biology is doing what the code predicted. Specifically, things called potentiostats for rigorous electrochemical testing.
Okay, 3 big cost centers. Let's focus intensely on that first one, the SynBio R&D, because there's a huge paradox here, isn't there? The report notes that raw DNA fragments, the basic building blocks, are incredibly cheap.
They are almost absurdly cheap now. We're talking as low as, what, 7 cents per base pair?
Yeah, meaning a simple 500 base pair sequence, a small genetic instruction, might start at just $49. That sounds like a really low barrier to entry.
It sounds low, but it's a phenomenal illusion of affordability. It's like looking at a pile of cheap raw lumber and trying to estimate the cost of building a functional, stable skyscraper from it.
Okay, explain that leap. Why the illusion?
Because that $49 gets you the raw ingredients, the inert chemical sequence. The cost absolutely explodes the moment you try to translate those raw, inactive fragments into a functional, stable genetic circuit that can be reliably inserted, expressed, and maintained within a living organism generation after generation.
So what's involved in that translation? What makes the assembly process so expensive?
Well, it requires complex multi-fragment assembly, stitching those cheap pieces together in the right order, and critically, the generation of custom vectors.
Vectors, what are they?
A vector is essentially the delivery mechanism. Think of it as the biological vehicle or maybe the factory floor where your genetic circuit is inserted so it can be copied and actually function inside the cell.
Okay. And making these vectors costs money.
Significant money. Just assembling, say, 3 DNA fragments into a standard off-the-shelf vector might cost around, ballpark, $600 to $750. But that's often not good enough for something like this.
Why not?
Because for the shifter protocol to be a permanent, reliable operating system for these microbes, you can't just rely on temporary, unstable bits of DNA called plasmids. They can get lost when cells divide. You need stable integration.
Meaning the shifter protocol code needs to be written directly into the microbe's main chromosome, its core operating system.
Precisely. And achieving that stable integration requires generating custom gene targeting vectors. These are highly specialized tools.
And presumably highly expensive.
Bingo. That's where the costs really jump. The report estimates the price range for generating these custom vectors, essential for stable integration, is sharply between $1,950 and $3,950 per construct, per functional genetic circuit.
Wow. Okay, let's break that down. The shifter protocol, conceptually, needs several parts, right? Something to sense fuel levels, something to sense toxin levels, something to tell the tricksters to speed up, something to tell them to slow down, maybe something to manage the physical connection to the electrode.
At least. You're probably looking at a minimum of 3 to 5 distinct complex genetic circuits that all need to work together reliably.
So if each one requires a custom targeting vector for stability, you're looking at a baseline expenditure of, what, roughly $6,000 to potentially $20,000 just for the custom SynBio services before you even start testing if they work.
Exactly. And that, the report stresses, is the optimistic best-case scenario where your initial designs actually work first time.
Which isn't guaranteed in biology.
Far from it. The report highlights this as the highest financial risk, failure in iteration. If those initial circuits fail to express correctly, or if their performance isn't stable or strong enough, which is incredibly common in SynBio R&D.
You have to go back to the drawing board.
You have to refine the design, commission new vectors, build them, test them again. Each cycle adds thousands more. The report estimates that a single circuit's effective cost can easily multiply to $12,000 or more if it requires multiple design-build-test cycles.
Ouch, that iterative refinement cost is brutal.
It is. It's the financial penalty for biology's complexity. And it often makes ambitious synthetic biology projects like this impossible for smaller labs or startups without significant funding.
And this complexity isn't just about getting the code right, is it? The report emphasizes that the functional requirements, what the circuits actually need to do, are often non-intuitive.
Absolutely. It's not just about making the microbes follow the shifter protocol's logic. It's about making them physically effective power generators.
Right. The report details optimizing the extracellular electron transfer pathways, ET. That's the mechanism the microbes use to actually push electrons out onto the electrode, generating current.
And optimizing ET involves modifying components far beyond just the core electron transport proteins, the wires inside the cell.
What else is involved?
They reference some benchmark research on a bacterium called Schoenella oneidensis MR1. It's a well-known electroactive microbe, a workhorse in this field.
And what did that research find?
The major, really non-intuitive finding was that achieving a massive 90% increase in current generation wasn't achieved by tweaking the internal electron wires. It was done by altering gene expression related to capsule polysaccharide synthesis, CPS, and biofilm formation.
Wait, hold on. Capsule polysaccharide. That's like the slimy coating on the outside of the bacterium, the biofilm matrix.
Exactly. That physical slime, the CPS, was actually acting as a kind of insulator. It was hindering the electron transfer to the electrode.
So it's like the bacteria were wrapping themselves in biological cling film, blocking the connection.
That's a great analogy. Think of it as biological resistance, or maybe like wet grout between the cell and the electrode. It adds impedance.
So a successful trickster agent, one that needs high output, high sigma, doesn't just need the internal drive, it also needs a genetic circuit designed to reduce the slime.
Essentially, yes. To manage this physical interface, by targeting the downregulation of CPS synthesis, you have to effectively clean the connection before you can efficiently send the signal, the electrons.
That is completely non-intuitive. You'd think optimizing the internal wires would be the key.
Most people would. And the research really validated the R&D risk here, too. They showed that a simple gene deletion mutant, just knocking out a CPS gene, failed to replicate the high current generation seen in a different mutant, where the gene expression was altered more subtly, maybe through a specific insertion.
Demonstrating that sensitivity again.
Extreme sensitivity. It proves you can't just use genetic scissors to cut and paste logic like software code. You need nuanced control over when genes are expressed, how much product they make, the timing, the dosage. It's analog, not just digital.
Which circles back to why you need that expensive iterative design build test cycle. Predicting success just for the DNA sequence alone is almost impossible. You have to test it in the real biological context.
Exactly. Okay, so that covers individual cell optimization. But the theoretical blueprint, the mythic biogrid, relied on the shifter protocol for coordinated, decentralized action across the whole grid, collective behavior.
Right. Not just one supercell, but a smart colony.
Which means, in the real-world prototype, this requires integrating quorum sensing, or QS, as absolutely critical infrastructure.
Quorum sensing, that's how bacteria talk to each other, right? Chemical signals.
Precisely. QS allows bacteria to sense their population density and coordinate group behaviors using signaling molecules called autoinducers. A common one is AI2.
So the biogrid prototype needs to use QS4.
For the colony to collectively sense key environmental changes, things like the concentration of their food source, acetate maybe, shifts in pH, perhaps even the overall current density being produced by the grid. And then crucially, in response to those collective signals, they need to modulate their internal ET circuits.
So QS is the biological mechanism that implements the shifter protocol's logic across the whole population. It's how they know whether to enter defense or aggression mode together.
You've got it. It's how the shifter protocol moves from being abstract computational code to becoming a living, coordinated, colony-level behavior.
Which means the system needs a synthetic genetic circuit that acts as a robust, stable receiver and emitter system for these chemical QS signals.
Correct. Integrating a sophisticated QS receiver-emitter system, like a LexP LSRB system, which detects AI2, requires building another dedicated synthetic operon. And for reliability, it absolutely must be integrated stably into the genome.
Don't tell me. This also falls into that highest cost category for SynBio services.
I'm afraid so. Once again, building and validating this kind of complex, stable construct lands squarely in that $1,950 to $3,950 per validated unit range.
So communication infrastructure is just as expensive as the core performance circuits.
At least. And arguably more critical for the system-level intelligence the simulation demanded. You simply cannot have a truly self-governing adaptive system without this communication layer, regardless of the cost. It's non-negotiable.
Okay. A sobering picture on the SynBio front. Let's pivot now to Section 4 in the report.
Yeah.
The physical fabrication and the budget for the active control infrastructure. The ACI needed to measure that, well, ACI score.
Right. So let's assume, hypothetically, we've successfully navigated the SynBio abyss. We've got our genetically stable, shifter protocol-enabled microbes ready to go. We still have to actually build the physical hybrid topology prototype for them to live in.
And the materials budget here isn't trivial either.
Not at all. As we touched on, MFC performance is intrinsically tied to the electrochemical interface, the electrode materials. Two components really stand out in the budget analysis due to their required purity and specialized nature.
First is the activated carbon felt, ACF. That's the main structural substrate for the electrodes, the scaffold.
Yes, and the report is adamant. You have to commit to the high purity stuff.
Why? What's the risk with cheaper felt?
The microbes are just too sensitive. Low-end materials risk outright prototype failure. They might contain impurities that are toxic to the bacteria or that interfere with their metabolic processes, or maybe they corrode and destroy that delicate biointerface where the electron transfer happens.
So cutting corners here is false economy.
Completely. The high-purity grades suitable for rigorous, reliable testing have a pretty sharp price range, anywhere from $1,550 up to over $3,450 for the kind of commercial rolls needed. Some specialized types can even hit $4,800. You just can't skimp on the foundational electrode material.
Okay. High purity ACF. What's the second key material?
Carbon nanotube solutions, CNTs. These are essential for enhancing the local electrical conductivity, especially right at those critical interface zones where the microbes meet the electrode.
And CNTs are notoriously expensive.
Yeah, they carry a high unit cost. Depending on the type and functionalization, they range from maybe $75 up to $300 per gram. And we're talking about the good stuff, highly functionalized, single-walled or double-walled nanotubes needed to maximize electron transfer efficiency.
So you can't just mix vats of it into the carbon felt.
Definitely not. Because of that high price, the physical design strategy has to be clever. The report suggests using CNTs sparingly, perhaps formulated as part of a conductive ink or composite coating, applied only where absolutely needed. Maximize the impact, minimize the volume and cost.
Which brings us to the manufacturing process for actually creating that hybrid topology shapes the spiral core inside the lattice shell. The report mentions a specific material for the biointerface.
Yes, the material of choice seems to be PDOT.PSS. It's a conductive hydrogel ink. Very biocompatible, good connectivity when wet.
And how do they propose fabricating the complex shape with this ink?
Through specialized 3D printing, specifically a technique called direct ink writing, or DIW. It allows precise deposition of these kinds of viscous inks or hydrogels.
Okay, sounds high-tech. Is it expensive?
Here's the kicker. The report notes that the cost structure for DIW fabrication is overwhelmingly dominated by specialized labor, not the actual volume of PDOT-PSS ink used.
Ah, so it's paying the technician running the advanced 3D printer that costs the money.
Exactly. Commercial DIW service labor rates can range anywhere from $17 an hour just for basic monitoring, up to well over $200 per hour for highly skilled technicians doing complex, multi-material printing. This becomes a massive, potentially opaque area of budgetary uncertainty that can balloon very quickly, especially for a complex geometry like the hybrid topology.
So how does the feasibility report suggest mitigating that potentially huge labor cost for DIW? You can't just print the whole thing out of cheap carbon felt.
No, they recommend an engineering compromise, a smart multi-layer strategy.
Okay.
They propose using the high-purity carbon felt as the low-cost bulk structural support. Think of it as the cheap scaffold providing the main shape, and then augmenting it with only a selectively fabricated thin coating of a PSS-CNT composite ink.
And that expensive composite ink is applied using DIW.
Yes, but only where it matters most. Restricted just to the critical biointerface zones where the microbes actually connect and transfer electrons. You only pay for the expensive materials and the highly skilled DIW labor exactly where that high-performance interface is needed. Everywhere else, you use the cheaper bulk material.
Clever. Targeted application of the expensive stuff. Okay, finally, we need to cover the budget for the control system, the active control infrastructure, or ACI, which is needed to actually measure and validate if the prototype achieves that target adaptive coherence index, ACI score, of 12.45 from the simulation.
Right. The report outlines a two-tiered approach for this ACI, designed to balance cost with scientific rigor.
Tier 1.
Tier 1 is passive monitoring. This is the cheap, cheerful, and continuous component. Multi-channel voltage monitoring across the different zones of the prototype. The good news is, this is highly feasible using standard COTSS electronics, like data acquisition HATs. Those add-on boards designed for modular systems like the Raspberry Pi. The report estimates that 2 mid-range DAQ HATs could cover all 12 monitoring channels needed for the prototype for under $400 total.
Okay, so continuous voltage logging, basic health monitoring is negligible in terms of capital cost.
Pretty much. Easy peasy.
But the real scientific rigor comes in Tier 2. Active characterization. This needs a much larger capital investment. Why can't the cheap COTS stuff handle this active analysis? What is active characterization?
Active characterization involves probing the system electrochemically to understand how it's working, not just if it's working. It requires techniques like cyclic voltammetry, CV, chronoamperometry, electrochemical impedance spectroscopy. These give you detailed information about the kinetics of the electron transfer, the efficiency, the reaction mechanisms.
COTS EQ boards can't do that.
No way. They're great for simple voltage logging, but for the precise, low current, controlled potential measurements needed for proper analytical electrochemistry, you need specialized instruments called potentiostats. They are absolutely non-negotiable capital equipment for this kind of R&D.
And potentiostats, I'm guessing, are not $400.
Not even close. Entry-level research-grade potentiostats start around $799 and can easily go up to $1,499 or more for basic units.
And for a 12-channel prototype.
The report argues convincingly that the 12-channel prototype necessitates 2 high-quality potentiostats, totaling somewhere between $1,600 and potentially over $3,000.
Why 2? Can't they just share one?
Time bottlenecks. Imagine you need to run a crucial validation experiment that takes several hours on one part of the hybrid topology. If you only have one instrument, all other testing grinds to a halt. Having 2 allows for concurrent validation and testing across different sections or under different conditions. It avoids massive delays in the R&D workflow. It's essential for efficient progress.
Okay, so capital investment in potentiostats is unavoidable for real validation. The report also flags something else. A hidden operational cost related to screen-printed electrodes, SPEs. They sound cheap.
They look cheap on paper. You can buy packs of bare SPEs for maybe $18 to $35. They're intended for rapid, disposable, in-situ sensing.
So what's the catch?
The catch is that their low unit price is completely deceptive. To be useful for sensing the specific things this system needs to monitor, like the acetate fuel source, the pH shifts, maybe even specific QS autoinducer molecules, those bare SPEs must be custom functionalized. Meaning you have to immobilize specific enzymes, antibodies, or other chemical reagents onto the electrode's surface. Then you have to calibrate them, validate them. It's a significant amount of specialized labor and requires expensive reagents, often far exceeding the initial cost of the bare electrode itself.
And they don't last forever in a microbial soup.
Exactly. They need continual replacement due to biofouling the microbes growing on them and interfering with the sensor. So it's not a one-off cost. It's an ongoing, high-labor, high-region operational expenditure that often gets completely missed or underestimated in initial capital budgets. It's hidden, but significant.
Okay. A lot of hidden costs and complexities in actually building and testing this thing. Let's try to bring it all together now with the integrated financial summary. Looking at all these estimated costs for the full advanced research prototype, the Tier 2 version with proper validation. What's the bottom line? What's the projected expenditure floor to actually get this thing built and tested, moving from code to working biological matter?
Okay, so crunching the numbers from the report, and this is explicitly excluding long-term personnel costs, university overhead, and those recurring operational costs like the SPEs we just discussed.
Just the core hardware, materials, SynBio services, and capital equipment.
Right. The projected expenditure floor, the absolute minimum starting point, is estimated at $18,800.
Okay, 18.8. That's significant, but maybe not astronomical.
But, and this is the huge caveat, remember the SynBio iteration risk. If those initial genetic circuits require refinement, that $18,800 figure rapidly scales up towards $38,000 or potentially even more. The range is wide because the synbio part is such a gamble.
So the major cost drivers, the things that swing that budget wildly, are clearly those high-end, custom synthetic biology services and the specialized high-purity materials needed for that non-toxic, efficient biointerface.
Without a doubt, those are the make-or-break cost centers.
Given that high risk and cost, the report logically concludes with a strategic mitigation summary. Some advice on how to actually succeed without breaking the bank.
Yes, it offers some key recommendations for navigating this minefield.
What are they?
First, they must dramatically reduce the synbio financial risk. The best way to do that is through rigorous, cheap initial screening of potential bacterial strains or basic circuit designs using rapid, low-cost electrochemical assays before they commit to commissioning those multi-thousand-dollar high-end custom operon services. Fail fast, fail cheap on the synbio front.
Makes sense. De-risk before you spin big. What else?
Second, they need to simplify the custom electrode geometry as much as possible. Every complex curve or feature fabricated using that expensive DIW printing adds significant labor hours and cost. Keep the high-performance zones simple and manufacturable.
Optimize the design for cost-effective fabrication.
Exactly. And third, when they do spend the big synbio money, they must prioritize the genetic circuits that fulfill the absolute core design mandates identified in the simulation and feasibility analysis.
Like our
Primarily, circuits that effectively manage that crucial cell-electrode interface, specifically targeting that capsule polysaccharide, CPS suppression we talked about.
Yeah.
And second, circuits that robustly incorporate the quorum sensing communication system. Those functions, clean connection and colony communication, are deemed the non-negotiable biological implementations required to make the self-governing system actually function as designed in the blueprint. Focus the big spending there.
Okay, that brings us pretty much full circle. This has been an incredibly detailed deep dive. We started with the, frankly, beautiful computational elegance of Skylar Fiction's mythic biogrid simulation.
Yeah, detailing the success of that hybrid topology spiral core, lattice shell, and the intelligence layer, the evolutionary protocol using the shifter logic.
Which together achieved that impressive adaptive coherence index of 12.45 in simulation. Proof of concept computationally.
And then we immediately slammed that elegant finding into the sobering financial and technical reality check. The inescapable conclusion is that the theoretical elegance relies entirely on successfully embedding that ethical and strategic operating system, the shifter protocol, into the living microbes themselves.
And that embedding process, the synbio, is complex, non-intuitive, and expensive, requiring custom services that cost around $4,000 per functional genetic construct.
A figure that, as we saw, can easily triple if the first design build test cycle fails, which is a very real possibility due to the inherent complexities of microbial genetic engineering.
So the final core design mandate seems sound. Build a hybrid topology, govern it with dynamic ethical flexibility via something like the shifter protocol. But its transition from simulation code to physical reality hinges completely on successfully navigating those complex, highly sensitive, and very expensive waters of applied synthetic biology, especially targeting those non-intuitive elements like biofilm production and the essential communication operons.
It's a fascinating challenge, but what I find truly profound here, thinking back to the simulation's core finding, is that the greatest determinant of the biogrid's ultimate survival and success wasn't its initial raw power capacity or even just its physical structure. It was its internal ethical flexibility.
The ability to dynamically shift strategy defense versus aggression based on the circumstances. Strategic self-control was key.
Exactly. It wasn't about brute force. It was about calculated adaptive behavior.
Which leaves us, and you the listener, with a really important, maybe even provocative final thought to consider long after this deep dive is over.
What does it truly mean for our future when the resilience and effectiveness of our physical energy infrastructure might depend less on raw horsepower or extractive capacity and more on the programmed ethical calculus, the calculated strategic adaptive behavior of the microscopic life forms powering it?